In this video, we are going to be talking about waves. Consider a horizontal rope as shown here. The horizontal dashed line is the undisturbed position of the rope. Let us place an oscillating device at one end of the rope. Using the oscillating device, let us create a sharp disturbance. The disturbance is seen to travel along the rope, and each point of the rope is disturbed successively, allowing energy to be transferred from one location to another. This type of disturbance that propagates from one place to another is called a wave, and in this case we call it a wave pulse because it is not periodic. If the rope is disturbed in a periodic manner, we see that all points along the rope are disturbed periodically as well. In this case, we have a periodic wave. Now let us have a look at what is happening to the particles of the rope. We have labeled the locations of successive particles as A, B, C, D, and so on. And the last point on the rope is labeled as Z. The disturbance caused by the oscillating device on the particle located at point A is passed on to the adjacent particle. The adjacent particle then passes the disturbance to the particle situated at point B, which then passes it to the particle adjacent to it. This process continues along the rope, allowing the disturbance to move from one location to another. If the disturbance on the particle situated at point A is periodic, then we have a periodic disturbance being passed from one particle to the next. This will result in each particle undergoing periodic oscillation about its undisturbed position. The propagation of a periodic disturbance from one location to another via successive periodic oscillations of particles, each about their respective undisturbed position, is called a periodic wave. Something very important to note here is that at no point do we see that a particle is permanently displaced from its equilibrium position, nor do we see particles flowing along the rope. Every particle simply oscillates about its undisturbed position. This is a very important aspect of wave motion, whereby energy is transferred from one place to another without the transfer of matter. From now on, we will restrict our study to periodic sinusoidal waves. Sinusoidal means in the shape of a sine curve or a cosine curve. Waves that require a medium to propagate are referred to as mechanical waves. For the wave on the rope is the medium. The particles of the rope oscillate to propagate energy. For wave on the surface of water, the water is the medium, and it is the particles of water that oscillate to propagate energy. And similarly, for a sound wave traveling in air, air is the medium and the particles of air oscillate to propagate energy. On the other hand, waves that don't require a material medium to propagate are called electromagnetic waves. For an electromagnetic wave, it is the electric field and the magnetic field that oscillate. For example, light is an electromagnetic wave. For now on, we will be focused on mechanical waves only. In fact, most of the features that mechanical waves possess are the same for electromagnetic waves. If we look at the wave on the rope, we can see that the shape of the rope is shifting to the right. The direction in which the shape is shifting is referred to as the direction of energy propagation. Let us freeze time so that everything stops moving. This is like taking a picture of the wave, so we have a snapshot in time. The shape of the wave repeats itself with distance along the direction of energy propagation. The minimum distance along the direction of energy propagation over which the shape of the wave repeats itself is called the wavelength lambda. the point A and the point E are separated by a distance equal to 1 lambda. The point A and the point C are separated by a distance equal to lambda by 2. And for point C and point D, they are separated by a distance equals to lambda by 4. Now let us have an x-axis in place pointing in the direction of energy propagation. The distance x of any particle from the point A along the direction of energy propagation can be defined. For example, the point A is at x equals to 0. The point C is at x equals to lambda by 2. And the point E is at x equals to lambda. When a wave is propagating, the particles of the medium are displaced from their undisturbed positions. So when we speak of displacement in the context of a wave, we are in fact referring to the displacement y of a particle of that medium from its undisturbed position. If we freeze time, the displacement y of a particle varies with distance x. Let us call this instant t equals to 0. What we see is that at x equals to lambda, which correspond to the particle at point E, we have y equals to 0. And for x equals to 3 lambda over 4, which is for the particle at point D, we have y equals to y naught, where y naught is the amplitude. The displacement y of a particle at a given position x varies with time as well. Let us focus on the particle at point B. And let us take the instant now to be t equals to 0. The displacement of the particle at point B is y equals to y naught at this instant. What we see is that as time progresses, its displacement y changes with time. In fact, the displacements of all particles vary with time when a wave is propagating. The time taken for a particle to complete a full oscillation about its undisturbed position is called the time period, denoted by capital T. The frequency f of a wave is then defined as a number of oscillations performed by a particle of the medium per unit time. The relationship between the time period capital T and the frequency f is f equals to 1 over capital T, and the unit of frequency f is Hertz. The angular frequency omega is then defined as omega equals to 2 pi over capital T, which can also be written as 2 pi f. And remember, the unit of angular frequency is rad per second. Now let us find out how we can calculate the speed of a wave. To do this, let us draw lines perpendicular to the direction of energy propagation called wavefronts. The distance between two consecutive wavefronts is equal to a wavelength lambda. The wavefronts move forward as time progresses. The distance moved by a wavefront per unit time is what we mean by the speed of the wave. To find the speed of the wavefront, let us look at the distance traveled by a wavefront in one time period, capital T. The distance covered by a wavefront in one time period, capital T, is equal to the wavelength lambda of the wave. Therefore, we can write v equals to lambda over capital T, where v is the speed of the wavefront. If we substitute 1 over capital T by f, then we have v equals to f lambda. And this equation basically is one of the most important equations in wave.